Progress.
Hello, everyone. In this video, I'm going to be going over the latent congruence model. So the latent congruence model is another form of a dyadic analysis, and it's an extension of the common fate model, which I have other videos posted on if you are unfamiliar with the common fate. But essentially, what the latent congruence model does is it conceptualizes. If you think back at the common fate, we have like a dyadic mean that affects both partners, but there's also individual variability. There's leftover, there's residuals within the information provided at the dyadic mean, right? So not everything that partner one and partner two in dyadic analysis they're going to share. So for example, me and my partner are going to have very probably similar reports on relationship quality, but there's also going to be individual differences between us. And so one of the ways in which we can kind of deal with those individual differences is by conceptualizing them as a difference score. So when we think about relationship quality between myself and my partner, we have what we kind of agree on, which would be our dyadic mean or our dyadic level, as we'll see it to be called. But then also we have a certain extent of disagreement within our relationship. We disagree to some extent on the quality of our relationship. And so that's what we're going to analyze with the latent congruence model. We are going to model what is shared, but also what is different between partners. And then we can use those variables to predict distal outcomes, even perhaps other difference scores, or they can be predicted by things. So the latent congruence model, again, brings again another new set of research questions that are focused on differences. And many of the discussion sections that we write and many of the theoretical sections we write in our introduction and lit review talk about disagreements or differences or discrepancies between partners, but very rarely do we actually test that at the dyadic level. And so again, that is what one of the purposes of the latent congruence model is. And so for those of you who are more visual learners, here is a visual representation of the latent congruence model. So this dyadic mean, again, for those of you who are familiar with the common fate model, is you have parameter or factor loadings fixed to 1 for both partners. That's this guy right here and this guy right here. And that creates a equally weighted average of partner 1 and partner 2. All right. But in the latent congruence model, we add this congruence component. And so what we do is we fix this loading to be 0.5. And then to get the contrast or the difference between partners, we fix this to be negative 0.5. All right. And then we correlate the latent congruence with the latent difference score and the dyadic mean. And generally, we're going to want this to be non-significant because it'd be kind of weird to have all the leftover information from the dyadic mean correlate to the difference score. And actually, we probably really don't want that. And if we have a significant correlation here, that means we might have some bigger problems in our model. And then I am going to show you how to estimate this model using observed and latent variables in Mplus. And so first we'll cover observed variables, which is depicted in this diagram down here, partner 1 and partner 2. But then you can also make these two variables here, latent factors to address measurement error. And as we'll see, you can also examine model data fit within your structural equation model using latent variables, which you will see we cannot do just using these observed variables. All right, so let's dig into Mplus. And so the first thing that I'm going to highlight is the syntax. So title, this is actually from another input file I just copied over, latent congruence model, observed variables. All right, so add a title. Again, this is not mandatory in Mplus, but it's always nice to have a title here and then also take notes in your title section. Your data command, you will always need this, and essentially you are telling Mplus where your data file is. And so if you have your input file and your data file in the exact same file location, kind of like I've done here, just we'll go over here. So you'll see all of my input files, and then you'll see my data file. All of that is in the same folder, and so you can just say file is and then name the data file because Mplus will automatically look within the same folder. But if it's located in a different folder, then you're going to have to type out that extension C colon / Dropbox or whatever that is. Right. So again, I strongly recommend creating a separate folder for each of your projects. And that way you can just do it this easy way and not make life so difficult for you. So in the data file in data2.dat, these are all of the variables that are in there, right? And you'll see at the top, I have all the male variables as well as just the dyad ID, which is just underscored with an M. Just based on the way the data were collected, I only kept the male dyad ID. We also had it for females, but again, it's completely repetitive. And so I just kept the males. And then you'll see again, underscore M to differentiate males. And then you have the exact same variables down here with female for the female partner. So these are going to be heterosexual dyads. And you'll see I have numbers at the end of every line. This is just my own way of when I'm importing, lots and lots of variables, just to I keep track of how many variables are in each line. And so I can just sum them up. And if that's the same number that are in my original SPSS file, then I'm good to go. Otherwise, that can cause some major headaches in your analyses, because if your variables are not put in the proper order, you are going to be analyzing different variables than you think you are. All right, and so now I'm going to move down to the use variables command. So use variables are, and we are going to tell Mplus what variables are actually going to be in our analysis. What variables are we going to pull from data2.dat into our actual model? Right, and so if you are using every single variable up here, so you're using every single one of these, this command is actually not necessary. So that's actually superfluous, and you can just do that. But alas, we are only using a couple variables, so we do need this use variables command. And as you see, we're only using two variables here. It's going to be the couple satisfaction index for males and the couple satisfaction index for females. Essentially, it's a 4-item scale that assesses overall happiness and relationship satisfaction among romantically involved partners or dyads. I specified missing data. We don't have a ton of missing data here, but we do have a few cases. And so I am telling Mplus that every variable within my data file that is -999 is a missing value, and it should not be viewed as an actual value. So I'll show you the data file really quickly. And so you'll see some -999s in here. This variable here has a lot of them because this is our marital length variable. And not all of the couples that we recruited are married, so they were obviously missing on marital length, but we have relationship length over here, which has a lot more complete data. So that's what it looks like in your Mplus data file. Okay. So down here, actually skipped one, ID variable. And so SEM is stored in wide format. Actually, so I guess I can pull that data file back up. So this is the dyad number right here. So dyad number 13, and then these first, I'll say 30 or 40 variables. These are probably all going to be males, and then somewhere around here, I don't know exactly where, from 15 on, are all going to be females. All right. And so, so we have males next to females in terms of data. So that's wide format. And so every row here is at the dyad level, right? So we have dyad 13 and we have the male and female partner data right next to each other, which is what you need in most, if not all, structural equation modeling um, programs. Right. And so I'm having an ID variable. This is really helpful if we have detecting potential outliers, if there's anything wrong with the data, then we can figure out what case might need to be dropped. If there's a missing value problem, this is always really helpful to have some form of an ID variable, and you want to have that in your rows. All right, so since we're in wide format, our rows are going to be dyads. So we have dyad ID. And then also I have the use obs command. All of this is under the variable command. Is I am telling Mplus to exclude these cases. So we have some potential people in the data set who just clicked through. And so through some previous analysis, some previous data management and poking around just to see kind of what is there, I am telling Mplus dyad ID underscore M. So that's the variable up here. That's this dyad ID variable and this dyad ID variable. NE is not equal to 159. So essentially, this is telling Mplus to exclude dyad number 159. And then if you want to exclude multiple people, then you just throw an and in between. And you can also do this. There are other commands within the use obs command. And you can integrate multiple commands and separate them by using the and statement. And so you can see I am letting go of case 159, 288, and 358. All right, so we're not using the define command at all in this analysis, but this is where you could create a composite. You can transform your variables. Really, you can manipulate variables in any type of way. And then in the analysis command, you actually don't need type as general. That's actually unnecessary. And most of the time, if you're just using maximum likelihood, you might not even need that. So you could exclude the analysis command altogether. But we are using robust maximum likelihood with Yuan and Bentler corrected standard errors. And so because that is due to non-normality, which can change your chi-square value, it can affect your standard errors. They can be too low, so you get prematurely happy when you get a significant value, but that's due to non-normality and has nothing to actually do with the parameter estimates or their standard errors because they are incorrect if there's a lot of deviation from multivariate normal distributions. And so to correct that, we are going to use robust maximum likelihood. So if you have complete data, then you can use MLM, and that provides Sator-Bentler corrections, or you can use MLR because most of the time that's going to be the most realistic estimator that you will use to address non-normality. The one time in which you probably would use MLM is if you did like multiple imputation beforehand, is the only time I can really think of that where you would use MLM. So we'll use MLR. And then now we're going to get down into the model command. And so in Mplus, to specify a latent variable, you use the by statement. And so we're creating the CSI difference score, and we're creating the CSI mean. Sometimes it's also called a level. And so based on the diagram I showed you earlier, this one, we're going to fix the factor loadings to be 1 for the dyadic mean. And so that's actually the second one. So we have the CSI mean, that's the created latent variable name by, and then we have female reports at 1. And this at 1 is what fixes it to 1. If you get rid of this, then it's going to be freely estimated. But we are constraining that unstandardized factor loading to be 1. And then we are doing the exact same thing for males, where their CSI, relationship quality scores, are also constrained to be 1. For the difference score, it's called the latent congruence model, but to me, it makes a little bit more sense for it to be conceptualized as a difference score because right now it's kind of a lack of congruence, is we have the females at negative 0.5 and the males at 0.5. And right now, this is just a completely arbitrary assignment. It doesn't really matter whether or not what partner you have at negative 0.5 and at 0.5. All it's going to do is flip your sign of your of the mean of this latent variable that we are going to estimate. So it's not going to affect results in any meaningful way. But I may talk about later when we begin to interpret this in the context of distal outcomes, it might make some more sense to have a specific person be a specific goal, either positive or negative. But for right now, it does not matter. All right. So we have our two latent variables specified. And then what we also need to do is insert some constraints on the observed variables. So we're going to enter constraints on these guys right here. And so as you can see, tau 1 equals 0 and delta 1 equals 0, and tau 2 equals 0 and delta 2 equals 0. Essentially, this is constraining the mean of partner 1 to be 0 and the mean of partner 2 to be 0, which is your tau, this one. And then you have your delta, which is your residual variance. And so we are constraining that to be 0 across partners. So essentially, that is actually one of the drawbacks of the latent congruence model, at least in my eyes, is that it conceptualizes unexplained variance by the mean, by this guy right here, as completely due to what is uncommon or different between partners, and we can't incorporate measurement error. So we're kind of conflating the difference score with measurement error. So we are assuming that that these observed variables here, which is couple satisfaction in our example, are measured with perfect reliability. All right. So again, I've never seen a scale measure above like a 0.98, and even that's exceptionally rare. I think our reliability is around between 0.90 and 0.92, so really quite strong. But that is going to insert some bias into our estimates. All right. So if you're going to use this model, that's something you're going to have to reconcile and to consider. And so we're going to fix all of that to 0. So essentially what we're doing by doing that is we're pushing all of the information around means and around variances up into the latent factors, right? And then we're also going to encounter, if we were to freely estimate these, we would be under-identified. So we would have negative degrees of freedom and our model wouldn't run. So these are necessary constraints in order to run the model. And then here, you see that I have in brackets the two latent variables. And essentially what I'm doing here is telling Mplus to estimate the means or the intercepts of these latent factors, right? So in latent variables, they're not observed in our data file, so we have to give them a mean and we have to give them a variance. And so we're doing so with the variance through these path constraints, and we're doing so with the mean through telling Mplus to freely estimate the mean and fixing the means to be 0. So all of that mean information is getting pushed up that factor loading. It's getting pushed up from partner 2 and partner 1 up into this latent congruence model. So it's going back across that one-headed arrow. All right, and then plot information, I'll actually delete this since we're not going to go into outliers here. And actually I can probably just delete plot altogether since, we'll look at the plots. Why not? We can look at the distributions of the latent variables. All right, so we can go ahead and save this and we can run it. And so the most important message is model estimation terminated normally, so we're good to go. We will have no degrees of freedom. So as I had mentioned before, if we had freely estimated the means and the variances or the residual variances more specifically of the observed variables, we would have -4 degrees of freedom. Our model would not run. We would not get standard errors. And so we could obviously not evaluate whether or not our parameter estimates were significant or not. And so in the observed variable latent congruence model, we are perfectly reproducing the variance covariance matrix. So this will always be 0, these will always be 1, this will always be 0, and this will always be 0. And so we don't need to worry about fit with the observed latent congruence model, which could be a good thing. It's one less thing we have to worry about, but also a bad thing because, again, as I said, there's no real way to evaluate the extent to which we have the ability to reproduce those variances and covariances. And it's kind of a cowardly way to go. So we are not essentially putting our theory in mortal danger. We are not actually evaluating to what extent our theoretical model is supported by the data, because again, everything that we can estimate is estimated. All right, so first we have our factor loadings up here, and then we have our covariance between the mean and the difference score, and it's non-significant. It's actually a little too close for comfort, but it is non-significant, which is good. We have our means, and these means are going to be of the latent variables. So our difference score is not significantly different from 0. So at first glance, that might seem like kind of a, that might be problematic, but it's actually in this model not problematic. It actually means that on average, the amount of disagreement across dyads is not significantly different from 0. All right. And so again, that could make some sense, especially with a variable like relationship quality. If you were to do something more like effective communication or conflict resolution, you might see some differences here. You would probably actually see there'd be greater disagreement because women in communication and conflict related measures tend to be a little more unhappy with the level at which those processes occur. But again, we're just doing relationship quality for demonstration purposes. All right, but yeah, so yes, essentially, this is perfectly okay that this is not different from 0. And as you can see, the positive estimate means men, since they are positive, report slightly higher levels of relationship satisfaction, relationship quality, which again, research has shown for decades and decades and decades that men tend to be, on average, happier than women are in their relationships. So we also have our mean, and this would be identical to what you'd find, in a common fate model. And so the average score is 20.128 on the CSI. All right. So these are intercepts. These were those taus we fixed to 0. Our residuals, again, those we fixed to 0. And then although we didn't request this in the syntax, Mplus will give us our variances. And so we have variances for both the difference score and the dyadic mean. And so for the dyadic means, it means there's couple-to-couple variability in how happy the dyads are. So you're going to have some couples, again, the unit of the analysis is couples here, some couples who are exceptionally happy, and then you're going to have some couples who are a little bit less happy, but maybe overall still happy. Then you're going to have those who are not happy and not unhappy, and then you're going to have those who are more unhappy, right? And so that's what this variances component is kind of telling us, is that there's variability in the levels of happiness in the dyadic mean. We also find that there are there's a significant variation in the difference scores. All right, so even though the mean, and on average, couples, the level of disagreement tended to not be significant, because the variance component of that latent factor is significant, it tells us that there's variation in the levels of disagreement. So again, some couples are going to be have very little disagreement. Other couples are going to have more and more and more disagreement. And if you go higher on the mean, it means there's greater disagreement, and males report higher scores. But if you go lower, then there's greater disagreement, and females report higher scores of relationship quality, right? So this is kind of where we're getting into latent means kind of being really, really important and being accurate in your interpretation of the variables. Because if we had flipped these dyad members, if we had put male as negative 0.5 and we had females at 0.5, and then we would have to throw a negative sign here, that means the negative sign, that means this mean becomes negative, which means if we're using this like predict a distal outcome, there's a different level of interpretation because a 1 unit increase in difference scores in the prediction of some distal outcome, likelihood of divorce or whatever it is, that now actually is moving us towards more and more agreement because it's negative. So 1 unit increase takes us from a negative value to a positive value. And so, again, depending on the outcome variable, I will flip the people in terms of who gets the negative sign, just for ease of interpretation, because I always want a 1 unit increase to represent a increased level of disagreement, not a negative value, and it increases to represent a level of more agreement. Because again, that's one of the tricky things with the latent congruence model. All right, so that is basically the latent congruence model with the unstandardized results. And if you want to know the standardized results, you can kind of scroll down here. But again, the variance components are going to be fixed to 1. And you are going to have your standardized means, but they're not going to give you really any different type of information. You just don't get any information about your variances due to, again, standardization, where when we standardize variables, our variances become 1 by default, and the latent means become 0. So that is the observed variable latent congruence model. But we can also throw in the latent variable latent congruence model, which essentially is the exact same thing, but we are using a latent variable which addresses measurement error and allows us to have evaluate model data fit. And so I'll delete some of this stuff just for ease of presentation. And so people aren't wondering why I have other variables in there when they're not actually in the model, they're commented out. Everything up here is exactly the same data set, same everything else. We have our missing variables, we have our dyad ID, we have our folks who were not so kind to us and didn't give us real data. But the only difference you'll see is that instead of the CSI 4, just the composite, we have the individual items from the CSI 4. All right, so this is item 1, 2, 3, and 4. And for the females, whoops. And then we have items 1, 2, 3, 4, and 5 from the males. And so what we're going to do is now, instead of going back to kind of this picture, instead of this being an observed variable represented by a rectangle, this is now going to be a oval or a circle, which indicates a latent variable. All right. And so what in the latent congruence model, you are presuming, and you should be testing measurement and variance across your constructs. And so I had done that already, and I found partial invariance. So item 1 for in the males was actually acting a little funky. The loading was significantly lower than in the females. And so I just released that constraint. I allowed that to be freely estimated. But you'll notice for every other variable, we have our by statements creating a latent variable. You see these labels at the end. And that means I am constraining those factor loadings, again, to be equal across groups. So previously you saw the at one, so that constrains it to be one. Here I am allowing the factor loading to be estimated, but it has to be the same for both men and women, which means this item is just as indicative of relationship quality for women as it is for men. A way to think about this, it's not exactly how it works, but you can think of this factor loading, the constraint to equality, as just the midpoint between the male and the female factor loading. So let's say it was 0.8 in women and 0.7 in men, then your factor loading for both of them would be 0.75. So essentially, again, a kind of a dyadic average of sorts. Again, that's way overly simplified, and that's not exactly how it works, but for the intents and purposes of this, that is a way to begin to understand what is happening by constraining those factor loadings to be equal. All right, so you'll notice I have a label here and not here. That's perfectly fine. You can also delete this. It's not really serving anyone any good. I just had left it in just for ease of analysis before. But again, it's inconsequential. All right. And so these are the latent variables for our relationship quality. And so now we have to do a very similar thing that we did in the observed variable latent congruence model. We are going to set the intercepts for each of those to be 0, right? Actually, I need to free that up. That was a mistake. When you have non-invariance at the factor loading level, you need to freely estimate that that intercept as well. But that's I have a different video on dyadic measurement and variance. And so that might be a good resource for you. So I'm not going to dive into the details now, but we do need to free up that intercept. All right, so now we are fixing those intercepts of items 2, 3, and 4 to be 0, and we're doing that for both male and females. Again, this is to push information about the mean from the observed indicators up into that latent factor, up to here. Right, we're going to push it up yet again here in a second. All right, so I've specified those latent variables and placed the appropriate constraints on the model. So now I'm going to create my latent congruence factors, and this is just copied and pasted from the observed variable syntax. There is nothing different other than slightly changing the variable names. Everything else is exactly the same. You'll see here, it looks kind of similar to the syntax before, but I've added a star just to explicitly tell Mplus to estimate the variances of the difference score and the mean score. So if you throw that star in there, that tells Mplus to freely estimate it. And then same thing with the mean of the latent variables. I want that freely estimated so I can get a dyadic average and I can get a dyadic difference score. And then again, I want to push that information from the means up from the individual items to the latent variable. And now I'm pushing that mean information from the latent variable up into the dyadic mean and the latent congruence score. So I'm going to fix the means to be 0 for male and female, and the same thing with those residual variances. Okay? And so again, the residual variances in this model, because again, go back to here, they're the dependent variable, right? Our latent variables are theoretically causing, in part, the levels of this variable. So this would actually be a residual. And so we're going to fix those to be 0. So all that information about the variances also goes up to the latent factor. And then what we are also going to do is co-vary the items with one another. All right. So when we think about non-independence in dyadic data, one of the ways in which we address that is through covariances of the residuals. So essentially, this is telling us, we're estimating or hypothesizing or suggesting that the way males respond to item 1 is not going to be completely independent from how their female partners also respond to item one. All right. Same thing with item two, item three, and item four. And so we're going to throw residual covariances on there. Even if these are not significant, I highly recommend you keep them on just to account for non-independence, and otherwise you're not accounting for independence of the items, and that little information contained in the residual, that's gonna be impacted within the factor loadings, within the variances, and within the covariances of the variable, specifically at the level of the difference score. So you might end up with biased variance and covariance estimates if even if these are not significant, that little amount of information can get out and can actually create havoc elsewhere in your model, because it needs to get out somewhere. And then finally, we're going to correlate our difference score with our mean score. Again, we can get rid of the plots, and we'll actually look at the plots. All right, so we'll go ahead and run this. All right, so input reading terminating normally, same thing with model estimation. All right, so we have degrees of freedom, again, because we have latent variables and we have more pieces of information in our model than we are estimating. We can evaluate the extent to which our data fit our hypothesized model fit our data, and it looks pretty good. This is pretty hard to get to be non-significant, which we want, and so this model is doing really quite a good job of replicating our variance covariance matrix. Our RMSEA is good. The 90% CI is a little high. We want that to be a little bit tighter, but overall, it's not horrible. Our CFI and our TLI are looking really good, 0.99, 0.989. Our SRMR is looking good. Again, that's a little higher than I'd probably want it, but overall, it's doing a really nice job at reproducing the characteristics of our data. All right, and so actually what I will show you real quickly is, let me modify this. Let's say we don't, remember I had this previously constrained, and if we impose that constraint, we fix that to 0, despite the factor loadings being different, right? We'll save it and we will rerun our model. Look at this. Our chi-square went up by something like 30, 35, almost 40. And so again, that was one little parameter that was being constrained to be equal, and it really shouldn't have been. And you can see how big of an impact it has on our model data fit. Our RMSEA is twice the size that it was. Our CFI and our TLI both went down by about 0.4 or 0.04, excuse me. Our SRMR it tripled in size. So you can see that even one little misspecification can have a pretty substantive impact on the model. So we'll scroll down to our residuals, and here is that value right there. So this is telling us, this is modification indices, telling us to freely estimate this mean. And so again, when we do, make this full screen again, we remove this constraint. And we scroll back down to those mod indices. All right, no modification indices. So that was the right parameter to remove. All right. Again, we have a good model fit. Now we can scroll down to our results. And as you can see, we have our model results here, our unstandardized ones. So remember back when we did the observed model, we had there's a negative covariance between the two latent factors, and it was negative 0.707, right? look at it now. That was the, or 0.077 was the p-value. Well, now it's 0.607. So a lot of that that precision was due to measurement error. We're getting such a high p-value relative to 0.607 due to measurement error. Right? And so again, that's one of the benefits of using a latent variable model is that you have measurement error and you're going to get much more precise estimates of your parameter estimates. And generally they're going to be larger when you're using latent variables because again, you're addressing measurement error, which tends to attenuate or reduce your parameter estimates. All right. And so here we have a couple of significant residual covariances. Again, we have a couple non-significant. Again, I would strongly recommend not freeing these up despite the temptation to add more degrees of freedom. We already have a good fitting model. Let's not play a game of whack-a-mole where we send some information off and it can wreak havoc and bias other parts of the model. All right, so here we have our difference score, right? So it's negative 0.005. Again, it's non-significant. Let's see, and we have women as negative again. So this means when we're using latent variables, women actually tend to report slightly higher levels of relationship quality, actually. So that's an interesting finding in and of itself, despite its non-significance. And then we have our dyadic mean, which is, again, significant. And again, here's our one intercept, or our item intercept, I should say, that is significant, or is freely estimated, I should say, right there and right there. All right, and then we have our variances. So again, we have variation in the difference score. So the latent variable difference score, or I'm sorry, the difference score using a latent variable indicators versus an observed variable indicator, they have the exact same interpretation. They just tend to be a little bit more precise. So again, here is from dyad to dyad on average, there is not a significant level of disagreement on relationship quality. That being said, there are dyad to dyad differences in the levels of disagreement. Right. So again, this is an average across every dyad, and this is the variability of that mean score, which is significant. So you are going to have some couples who are happier or who have greater levels of disagreement than others. And likewise, we have the CSI mean. The dyadic mean is significantly different from zero, and there is dyad to dyad variability in the level of relationship quality, again at the dyadic level. So again, this is the latent congruence model. Again, you can further build this out by estimating two separate latent congruence factors and have them predict one another, or you can have them predict a distal outcome. You can predict what causes disagreement in relationship quality. And that's a really, I think, really interesting set of research questions. As long as you have these variances being significant, then this can be a dependent variable. If this is a constant, if this is not, if these are not significantly different, then you really probably shouldn't use predictors. That being said, some people have argued once you add in a predictor, let's say this was like 0.10, this is 0.10, so kind of not marginally significant. I'm not even sure what that means, but the p-value isn't 0.90. Once you add in a predictor, these variances can actually drop to significance. So you can actually add in covariates to once the variance accounted for by those covariates is considered, that variance estimate actually becomes significant, and you can use other variables. So it's not again an end all be all, but you will see some people make that argument. One final thing I will say on the difference score is when we think about difference scores, we're kind of assigning people to create this difference score by male and female. And so one of the things that can happen when, especially when we have a non-significant difference score, is because we have variability, we're going to have most likely we're going to have some couples where the female is higher on relationship satisfaction than the male. And then we're going to have some couples where we're going to have male is higher than the female on relationship satisfaction. And so when you put those two groups of people, let's say we had 100 couples where the female's higher and 100 couples where the male's higher, you put them together, this can create a non-significant mean, right? So because it's again essentially a weighted average. And so so when you add, let's say the 100 females was negative, like the estimate was negative 0.2 and the males was 0.2. When you average those together, it comes out to be 0. And so there's some more nuance within the latent congruence model. And we don't really want to kind of begin to make really strong inferences saying that all females in the study reported higher levels of relationship quality than males, because that's simply not true. It's just on average. It means that when you look at all the female relationship quality scores, it's just slightly higher than the males. But what we could realistically have is, well, actually, I should say that's one possibility where, and I would say it's unlikely, but you have every single female in this sample be 0.005 units higher. That's one possibility in the interpretation of this score. But the other interpretation, as I had just mentioned, is that it might be that for a lot of couples, for half the couples, probably male is higher, and for the half couples, the female is higher, but the female is just a little bit higher. That the more their levels of satisfaction, their levels of satisfaction is just a little bit higher than males, right? So we don't want to make extremely strong definitive statements about the mean score because it has two different possible interpretations, and you have to dig further into your data in order to understand what is the nature of this difference score. Because again, it could be that all the females are just a little bit higher, or it could be roughly half the females are higher than the males, and roughly half the males are higher than the females. But those females, when they're higher, is just a little bit higher than the males. Right? And so the last thing I'll show you is data visualization. So we can go up to view plots, and we'll just take a look at the latent variable distribution plots. That's what I get from plot 3. All right. And we can look at these. So here is the distribution of CSI for women. Again, it's highly, highly, highly skewed, which again is why in part we use robust maximum likelihood. Same thing with males, which again makes perfect sense. If you are more in the middle of relationship quality, you're probably going to leave that relationship because it means you're not really all that happy. And so again, it makes perfect sense that we'd have a really, really skewed distribution. So our difference score, so we have a normal looking distribution, but we have a pretty excessive buildup at 0 or just around 0. But then it's kind of fans out after that. But again, just perhaps a standard deviation away from the mean, plus and minus, those difference scores get substantially smaller. So not terrible, but certainly not a normal distribution. We would expect the scores to be close to the distribution look something like this, more so than this. All right, and then the mean, of course, you put two very skewed variables together, you're probably going to get some more skewness. It actually looks a little bit better. And actually kind of what I am seeing, and again, people are probably going to yell at me for this, is I'm seeing some profiles. I'm seeing kind of a little normal distribution right here. I'm seeing a little normal distribution right here. I'm seeing a little normal distribution right there. And then we got these people at the end who are just exceptionally happy. So there might be profiles of dyadic means that we can examine, but that is a another for another day. But hopefully this has been helpful in helping you estimate, again, a one variable latent congruence model using both latent and observed scores. Thanks very much.